Alright, let's go. Number 10. The Clouds of Venus. In 1967, the Soviet Venera 4 probe plunged into the atmosphere of Venus and transmitted data back to Earth before being crushed by pressure 90 times greater than anything at sea level. Scientists expected hell. What they got was hell, except for one narrow band of sky sitting between 48 and 60 kilometers above the surface, where the temperature hovers between 0 and 60 degrees Celsius, and the atmospheric pressure matches a comfortable afternoon on Earth. Venus is by almost every measure the most hostile planet in the solar system. Its surface bakes at 465 degrees Celsius, hot enough to melt lead. Its clouds are made of sulfuric acid. Any probe we've ever landed there has been destroyed within hours. For decades, scientists wrote it off entirely as a candidate for life and moved on to more promising targets. Then, in September 2020, astronomer Jane Greaves of Cardiff University announced something that stopped the scientific community cold. Her team had detected phosphine gas in the Venusian cloud layer, a molecule that, on Earth, is only produced by industrial processes or by living organisms. No known chemical reaction involving Venus's clouds, surface, or sunlight could account for its presence. The detection was later disputed, the data re-examined, the signal contested, but it refused to disappear entirely. The idea that life might float in Venus's clouds is not new. Carl Sagan and Harold Morowitz proposed aerial microbial life in that temperate cloud band as far back as 1967. Microbes on Earth survive in clouds, in acid, in near vacuum. The chemistry of Venus's atmosphere remains poorly understood, and the phosphine question has not been definitively closed. What makes Venus so unsettling as a candidate is how long we dismissed it. The most Earth-like conditions in the inner solar system may not be on Mars. They may be drifting right now in the clouds of the planet we once called our twin. Number 9. Titan, Saturn's moon. When NASA's Cassini spacecraft completed its final mission on September 15, 2017, plunging deliberately into Saturn's atmosphere to avoid contaminating its moons, it left behind a world that had spent 13 years confounding every expectation scientists brought to it. That world was Titan, Saturn's largest moon, a place with rivers, lakes, rain, and weather systems where not a single molecule of the liquid involved is water. Titan was discovered by Dutch astronomer Christian Huygens in 1655, but for 3.5 centuries it was little more than a smudge in a telescope. When Cassini arrived and ESA's Huygens probe descended through Titan's thick nitrogen atmosphere on January 14, 2005, the most distant landing humanity has ever achieved. It revealed something extraordinary, a world that looked almost familiar, but was built from entirely different materials. The lakes and seas of Titan are filled with liquid methane and ethane. It rains methane. Rivers of methane carve channels into ice as hard as rock at minus 179 degrees Celsius. In 2015, scientists at Cornell University proposed that cell membranes called azotosomes could theoretically form in liquid methane, structures that could perform the same function as the lipid membranes in every living cell on Earth, using an entirely different chemistry. No mission has yet found life on Titan, but NASA's Dragonfly rotorcraft, currently scheduled to arrive in the 2030s, will land on the surface and investigate its complex organic chemistry directly. Titan's atmosphere already contains the raw ingredients, nitrogen, carbon, hydrogen, for prebiotic chemistry on a massive scale. Titan doesn't just expand the definition of where life might exist. It challenges the assumption that life needs water at all, and if that assumption is wrong, the number of potentially habitable worlds in the universe doesn't grow by a little. It grows beyond calculation. Number 8. Triton, Neptune's moon. On August 25, 1989, NASA's Voyager 2 spacecraft made its closest approach to Neptune's largest moon, Triton, the only close encounter humanity has ever had with this remote world, nearly 4.5 billion kilometers from the sun. Scientists expected a frozen, inert body, a relic from the early solar system preserved in perpetual cold. What Voyager's cameras revealed instead made planetary scientists lean forward in their chairs. Triton is one of the coldest surfaces in the solar system, sitting at approximately minus 235 degrees Celsius. It orbits Neptune backwards, a retrograde orbit that no moon formed in place could maintain, indicating Triton was captured from the Kuiper Belt billions of years ago. That violent gravitational capture and the tidal forces that followed generated enormous heat deep within the moon's interior. It is a world that should, by every measure, be completely and permanently dead. Yet Voyager 2 photographed active geysers on Triton's surface, dark plumes of nitrogen gas shooting 8 kilometers into its thin atmosphere, leaving dark streaks across the frozen plains. Activity, energy, something driving material upward from beneath. Tidal heating from Neptune's gravity, planetary scientists concluded, is still at work inside this captured wanderer, flexing its interior and keeping something warm underneath. If tidal forces are generating heat within Triton's core, the possibility of a subsurface liquid ocean similar to those proposed for Jupiter's moons cannot be dismissed. No follow-up mission has visited Triton since 1989. Everything we know comes from a single flyby that lasted hours. A world that orbits backwards, erupts geysers at temperatures that should permit nothing, and may hide an ocean beneath its frozen skin. And we have seen it up close exactly once for a single afternoon, 35 years ago. Number 7. Callisto, Jupiter's moon. For most of the 20th century, Callisto was the solar system's overlooked moon, a battered ancient world covered in craters dating back 4 billion years, with no signs of geological activity, no volcanic history, and no reason to generate any particular scientific excitement. Then, between 1996 and 2001, NASA's Galileo spacecraft made multiple close passes, and the data it returned quietly rewrote Callisto's story. Callisto is Jupiter's second largest moon, first observed by Galileo Galilei in January 1610, alongside its 3 famous siblings. Its surface is so heavily cratered that it represents one of the oldest, least altered landscapes in the entire solar system, a record of early solar system bombardment preserved in ice and rock. Nothing about its appearance suggested anything interesting was happening below the surface, but Galileo's magnetometer detected something unexpected. As the spacecraft flew past, the moon was distorting Jupiter's magnetic field in a way that indicated a conducting layer somewhere beneath the crust, the same signature a saltwater ocean would produce. A body of liquid water, scientists concluded, likely lies somewhere between 100 and 200 kilometers below Callisto's ancient surface. No one has explained precisely what is keeping it liquid, since Callisto lacks the obvious internal heating mechanisms of its neighbor Europa. What makes Callisto scientifically significant goes beyond the possible ocean itself. Unlike Europa, Callisto sits outside Jupiter's most intense radiation belts. It is quieter, more accessible, and safer for both potential life and future spacecraft. A moon that appeared completely dead turns out to potentially harbor the same ingredient that dominates every discussion of life elsewhere. If even the solar system's most forgotten moon is hiding an ocean, the question stops being which worlds might have liquid waters and becomes which ones don't. Number 6. Ganymede, Jupiter's moon. In March 2015, researchers using the Hubble Space Telescope turned their attention to Ganymede, the largest moon in the entire solar system, larger than the planet Mercury, and watched its auroras move. That movement, subtle and precisely measured, told a story about what lies beneath the surface that no drill, no probe, and no landing has yet confirmed directly. Ganymede was discovered by Galileo Galilei in January 1610. It has a diameter of 5,268 kilometers, its own intrinsic magnetic field, the only moon in the solar system with one, and a surface of ancient dark terrain interspersed with younger, grooved bright regions. It had long been suspected of harboring a subsurface ocean based on Galileo spacecraft data, but the Hubble observation provided the clearest evidence yet. The rocking of its auroral belts was being dampened, precisely as a deep, electrically conducting saltwater layer beneath the ice would dampen them. The ocean that Hubble's data implies is not a modest thing. Models suggest it may extend up to 800 kilometers in depth, 10 times deeper than any ocean on Earth. If accurate, Ganymede contains more liquid water than every ocean, sea, lake, and river on our planet combined, sealed beneath an ice shell and kept in the dark for billions of years. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in April 2023 and is currently en route to the Jovian system, with Ganymede as its primary long-term target. It will enter orbit around the moon in the early 2030s, becoming the first spacecraft ever to orbit a moon other than our own. The largest moon in the solar system may also be its largest ocean, and we have never once been close enough to look inside. Number 5. Ceres, the dwarf planet. On March 6, 2015, NASA's Dawn spacecraft eased into orbit around Ceres, the largest object in the asteroid belt, a dwarf planet 940 kilometers across drifting between Mars and Jupiter, and immediately began returning images that no one had predicted. Scattered across the floor of a large impact crater called a crater were bright, gleaming spots, reflecting sunlight back into space from the middle of an otherwise dark and battered landscape. Scientists were puzzled. Then the analysis came back. Ceres had long been considered one of the solar system's most inert bodies. A rocky frozen relic from the early solar system, too small to maintain geological activity, too far from the sun for liquid water, and too ancient to hold any surprises. Dawn was sent to characterize it, not to be astonished by it. The bright spots were sodium carbonate, salt deposits left behind when briny water reached the surface and evaporated. Not ancient water. not water that last moved billions of years ago. In August 2020, a study published in Nature Astronomy confirmed what the deposits implied. A saltwater reservoir approximately 40 kilometers beneath a Cater crater, still liquid, still mobile, still pushing material toward the surface in geological terms that suggest activity within the past few million years, essentially recent by planetary standards. Ceres may be up to 25 to 30% water by mass, proportionally more than Earth. Its interior appears to be warmer and more dynamic than its dead exterior suggests. Whatever is driving that internal activity, residual heat from formation, radioactive decay, some combination of both, has kept liquid water alive inside a world that receives less than a tenth of the sunlight Earth does. A dwarf planet alone in the asteroid belt, quietly seeping brine toward its surface, is not what anyone expected to find, and it demands that we reconsider every small, cold, supposedly dead world we have already dismissed. Number 4. Mars. On August 6th, 2012, NASA's Curiosity rover touched down in Gale Crater, Mars, in a landing so precisely engineered it required a rocket-powered sky crane lowering the rover on cables in the final seconds of descent. Within months of arrival, Curiosity had found rounded pebbles at the base of an ancient streambed, proof that water had not merely visited Mars but had flowed there persistently, in rivers deep enough and fast enough to smooth rocks over millions of years. Mars today is a frozen desert with an atmosphere so thin it offers almost no protection from radiation. Its surface temperature averages minus 60 degrees Celsius. Liquid water cannot exist there for long. But Mars was not always this way. The planet had a global magnetic field that collapsed roughly 4 billion years ago, stripping the atmosphere away over hundreds of millions of years. Before that collapse, Mars almost certainly had a warmer, wetter surface. Rivers, lakes, possibly oceans. Life had the same window of opportunity there as it had on early Earth. In July 2018, a team using the ESA Mars Express Orbiter's Marsus radar instrument announced the detection of a liquid water lake approximately 20 kilometers wide, sitting 1.5 kilometers beneath the South Polar ice cap. Kept liquid by dissolved salts and geothermal heat, the lake, if confirmed, would be a direct analog of subglacial lakes beneath Antarctic ice on Earth, several of which harbor microbial life. In June 2019, Curiosity detected a spike in methane in the Martian atmosphere, whose origin remains unexplained. Methane breaks down quickly in Martian conditions. Something is producing it now. NASA's Perseverance rover landed in Jezero Crater, a confirmed ancient lakebed, on February 18, 2021, and has been caching rock and sediment samples ever since, samples that may eventually be returned to Earth for direct analysis. Mars does not need to harbor life today to be the most important astrobiological target in the solar system. It only needs to have had the right conditions long enough, and the evidence says, without serious dispute, that it did. Number 3. Enceladus, Saturn's moon. In 2005, NASA's Cassini spacecraft was conducting a routine flyby of Enceladus, a small, ice-covered moon of Saturn, just 504 kilometers across, small enough that it could fit within the borders of France, when its instruments detected something that had not appeared on any mission plan. Enormous plumes of water vapor and ice particles erupting from the moon's south pole and venting directly into space, creating one of Saturn's rings with the material they expelled. Enceladus had been considered unremarkable. Its small size suggested it should have cooled and frozen solid billions of years ago. Its brilliant white surface, the most reflective in the solar system, indicated a fresh coating of ice, which was unusual, but not immediately alarming. Nothing in its profile suggested that beneath that frozen crust, something was violently alive. Cassini flew through those plumes multiple times. Each pass returned data that deepened the mystery and raised the stakes. In 2014, NASA confirmed a global subsurface ocean beneath Enceladus's ice shell, roughly 10 kilometers deep, sitting beneath a crust 30 to 40 kilometers thick, kept liquid by tidal heating from Saturn's gravity. In April 2017, Cassini detected molecular hydrogen in the plumes, a chemical signature of active hydrothermal vents on the ocean floor, the same geological process that, on Earth, supports entire ecosystems of life with no sunlight whatsoever. In June 2018, complex organic molecules were identified in the plume material, including carbon chains of more than 10 atoms, the building blocks of biological chemistry, liquid water, a chemical energy source, organic molecules, and a moon that is actively venting its ocean contents into space, placing a free sample within reach of any spacecraft equipped to catch it. Enceladus is not asking us to speculate. It is not asking us to drill through miles of ice or land on a hostile surface. It is ejecting the evidence directly into space, and all we have to do is fly through it and look. Number 2. Europa. Jupiter's moon. In 1979, Voyager 2 sent back images of Europa, one of Jupiter's 4 great moons, first observed by Galileo Galilei in January 1610, that left planetary geologists struggling to explain what they were seeing. Europa's surface had almost no craters. Its terrain was a tangle of brown-stained fractures, ridges, and chaotic broken slabs of ice, resembling nothing so much as the surface of a frozen sea that had cracked, shifted, and refrozen countless times. It was, scientists slowly concluded, young. And if the surface was young, something was renewing it. Europa has a diameter of 3,121 kilometers. Its surface ice is estimated to be between 15 and 25 kilometers thick, and it is believed to be geologically no older than 40 to 90 million years. Extraordinarily recent for a moon formed 4.5 billion years ago. Beneath that ice, Jupiter's tidal forces flex the moon's interior constantly, generating heat. That heat, planetary scientists concluded, is maintaining a global liquid ocean 60 to 150 kilometers deep, containing by volume more liquid water than every ocean on Earth combined. In 2012 and again in 2016, the Hubble Space Telescope detected what appeared to be water vapor plumes rising above Europa's south pole, hinting that the ocean may, like Enceladus, be venting material toward the surface. The detections were not definitive, but they suggested that Europa's ocean may not be as sealed and inaccessible as its thick ice shell implies. Where Europa's ocean contacts its rocky sea floor, tidal heating could be driving hydrothermal chemistry. The same chemistry that surrounds the deep ocean vents, where life flourishes in the complete darkness of Earth's abyss. NASA's Europa Clipper launched on October 14th, 2024. It is in transit now, on a trajectory toward Jupiter, carrying 9 scientific instruments designed to characterize the ice shell, probe the ocean beneath, and assess the moon's habitability in unprecedented detail. It is expected to arrive around 2030. Everything that makes a world capable of supporting life, liquid water, chemical energy, organic chemistry, time, appears to be present beneath Europa's fractured plains, and the mission sent to investigate it is already on its way. Number 1. What life on Earth tells us about the solar system. On a February day in 1977, the deep-sea submersible Alvin descended to the floor of the Pacific Ocean near the Galapagos Islands, approximately 2,500 meters below the surface, where no sunlight reaches and the pressure would crush an unprotected human body in an instant. The scientists aboard expected a cold, barren seafloor. The deep ocean at the time was considered one of the least hospitable environments on Earth. Then the lights of the submersible swept across the rocks ahead, and the team stared in silence at something biology had never prepared them to see. Life. Extraordinary, dense, thriving life. Tube worms nearly 2 meters long. Clams, shrimp, microbial mats coating every surface. Clustered around cracks in the seafloor were superheated water, laden with hydrogen sulfide and minerals, poured out of the Earth's interior at temperatures that should have been lethal. None of it used sunlight. None of it depended on photosynthesis. The entire ecosystem ran on chemical energy from the planet's own heat, in the crushing dark, at pressures and temperatures that had been considered definitively incompatible with life. That single discovery, in a single afternoon in 1977, began dismantling the framework scientists had used to define habitability for a century, and it has not stopped. Microbes have since been found living 3 kilometers underground in South African gold mines, metabolizing at a rate so slow they divide once every few thousand years. Organisms survive in Antarctic brine channels at minus 20 degrees Celsius. Deinococcus radiodurans, a bacterium, withstands radiation doses hundreds of thousands of times greater than a lethal human dose. Tardigrades, microscopic animals less than a millimeter long, have survived direct exposure to the vacuum of space. Every time science has drawn a boundary around the conditions life requires, something alive has already been found on the other side of it. This matters enormously for the worlds described above. Every subglacial ocean on Europa or Ganymede has a direct analog in the liquid water lakes beneath Antarctic ice, lakes that harbor microbial ecosystems in total darkness. Every hydrothermal vent proposed for Enceladus' seafloor mirrors the vents where tube worms flourished in 1977, before we thought such a thing was possible. Every methane lake on Titan is now evaluated against the knowledge that life on Earth has colonized environments that once seemed chemically incompatible with biology. The solar system's candidate worlds are not being assessed against a theoretical standard. They are being assessed against a growing catalog of real places on this planet where life refused to accept the limits we assigned it. The search for life elsewhere in the solar system is not, at its core, a search for another Earth. It is a search for the conditions that life on this Earth has already proven it can exploit. liquid water, chemical energy, time, and shelter from the worst that a hostile environment can inflict. Every one of those conditions exists, to some degree, on at least one of the worlds in this list. Some of them exist on several. The Alvin team went down to the seafloor in 1977, expecting emptiness, and found abundance. The lesson has not changed. Every time we have decided where life cannot exist, life has already been there. And the solar system, it turns out, is full of places we haven't looked yet. If you want to see more videos like this, click the video on screen now and make sure to subscribe.